Okay, I'm happy to welcome our last speaker of the day, Yuanyuan Feng from Penn State University. And she's going to tell us about dissipation enhancing flows and applications to Kuramoto Sivashinsky Equation.
Thank you. Thank you for the introduction, and also many thanks for the organizing committee for the kind invitation. So today I will first introduce the dissipation enhancing flows, and then talk about the applications, mainly with the applications to the Kuramoto Sivashinsky equation. So we know in compressible fluids, stirring induces mixing by filamentation and facilitates the formation of small scales. And diffusion, on the other hand, effectively dumps the small scales. So an important part of my study is to find how stirring would help dissipate the energy. So let's look at a simple example in our daily life. So suppose we want to add some milk into a cup of coffee. So to help the milk and coffee well mixed, we usually use a stirring stick to facilitate this process. So usually, what would matter this process? So one thing is about the direction of the velocity. So you can imagine moving the stirring sticks circularly would bring better effect than just moving the stirring stick up and down. Another factor is about the amplitude of the velocity field. Intuitively, the larger the velocity field is, the better result it would bring. So to quantify the interaction between the diffusion and the mixing, let's look at the energy decay in advection diffusion equation. So here, theta satisfies the advection diffusion equation. We look at this. We study this equation on the torus. So theta represents temperature in the fluid, and V is some incompressible flow, which means divergence of V is 0. And for the regularity, usually we ask at least we ask for Lipschitz regularity. Here, kappa represents the strength of the diffusivity. Usually, we are mainly interested in the range when kappa is much smaller than 1. For this equation, we assume periodic boundary conditions and restrict our initial data to be mean-free. So since V is divergence free, so if we restrict the initial data to be mean 0, then we can see that the theta would always have mean 0, right? So theta would always lie in this mean 0 space. Through basic energy estimate, by using Poincare inequality, we have the L2 norm of theta decays at a rate of e raised to negative kappa times lambda 1 times t times the initial L2 norm. Here, lambda 1 is the principal eigenvalue, which is strict positive, and which is a constant and strict positive constant. So can we improve this rate? The answer is yes. Exponential decaying rate can be improved as e raised to negative kappa times h kappa times time times the initial energy, where h kappa is some function depends on kappa, and which goes to infinity as kappa goes to 0. Here, h kappa can be explicitly written through sufficient mixing flows. What do I mean by saying sufficient mixing flow? I will define this later. So, okay, let's first look at the lower bound of this of the energy of the L2 norm. So Peng in 1998 proved that the L2 norm is bounded below by exponential of minus here I forgot constant c minus constant C times kappa times some quantity depending on the initial data times gamma raised to power T minus A. So here, gamma is some coefficient strict greater than 1. So we can see this is a double exponential lower bound. So exponential and gamma 2 times, right? Is the energy lower bound is double exponential in time. The optimality is in continuous time is open. So while Miles and Dorian in 2018, they did some numerical simulation and suggest that double exponential decay is not possible on the torus in continuous time. Well, with my advisor Gautam Yer and in 2018, we proved that double exponential decay is sharp in discrete time, where we consider the pulse diffusion model, which is defined as theta n plus 1 equals e raised to kappa Laplacian times Laplacian act on theta composed with phi. So that means we do one step. For one step we act on the map phi, and then for another time step we act on we put the diffusion operator here. So we prove that if phi is a cut map or some torus automorphism in general, then the energy decay of this pulse diffusion model has a double exponential upper bound. So let's then look at the upper bound of the continuous system. So let's recall that from Poincare inequality, we have the basic energy decay, which is e raised to negative kappa times lambda 1 times the initial L2 energy. If we define the dissipation time tau star as the least amount of time, such that after this amount of time, all the energy would decay to 1 over E of the initial L2 energy. By this definition, we can clearly it implies that the L2 norm is bounded by e raised to negative t divided by tau star times the initial L2 norm. This just because of the definition of the dissipation time. And from the basic L2 energy decay, we can see that the dissipation time tau star should have a natural upper bound, which is 1 over kappa times lambda 1, right? Or we can say this upper bound is of order big O of 1 over kappa. And we can see that beta bound of tau star would improve. By this definition, beta bound of tau star can will imply faster exponential decay rate for L2 norm. So next, we would to study the L2 energy bound, we would instead look at the bound for the dissipation time tau star. So for tau star, we have the elementary bound, which is 1 over kappa times lambda 1. So Konstantin Kislev, Rizik, and Zlatos at 2008, they proved that for V is time independent, kappa times tau star goes to 0 as kappa goes to 0 is equivalent to the transport operator V dot gradient has no eigenfunctions in H1. Such flows are called relaxation enhancing flows. And of course, weakly mixing implies relaxation enhancing, but not conversely. For this rate, they didn't give any information on the rate at which kappa times tau star goes to 0. The whole kappa times tau star goes to 0. That's to say tau star is of order little o, or 1 over kappa, right? So for us, we want to give a rate at which this convergence happens. To give a rate at which this convergence happens, we first want to introduce the mixing rate. What is the mixing rate? So let phi be the flow map of V. So that means partial T phi equals V of phi of T, and phi SS is the identity map. This is the definition of the flow map. What is mixing? Mixing is some mixing is a concept that comes from the dynamical theory, right? It says it would introduce ergodicity. What is ergodicity? Ergodicity means that the time average goes to converges to the space average, right? So mixing is stronger than that. So mixing says that, say, if is the space average of F is 0, then say a map phi, the flow map phi is mixing. That means F composed with the flow map phi should go to 0 in some things. Since V is incompressible, so that means the L2 norm or F composed with the flow map is conserved. So that means F composed with the flow map phi can only converge weakly to 0. So mixing actually means for any for any F and G in L2 with mean 0, then the correlation F composed with phi and G this correlation goes to 0, right? So what is mixing rate? Mixing rate, we introduce the mixing rate to be the rate at which the above convergence happens. This convergence happens. So first we want to we have a rate function, say call it H. H is positive, decreasing, and disappears at infinity. So this we call it mixing rate function. V is mixing with rate H. That means the correlation F composed with phi and G, this is always bounded about by the mixing rate function H times some norm of F times some norm of G. So what norm X can be put here? Can we put L2 norm? No. If X is L2 norm, then by duality of inequality, by duality, this would since the L2 norm is always conserved, right? So that by duality, then the rate function can only be chosen to be 1 here. So we want to have a decreasing rate function which disappears at infinity. So we have to choose a norm X stronger than L2. So in PDE, we usually choose H1 norm. So actually here, H1 norm can be replaced by any H alpha norm with alpha positive. By duality, this actually tells us the H minus 1 norm of F composed with the flow map is always bounded by the rate function times the H1 norm of F. So we just, this is is obtained from this condition, right? Just by duality. So some people in PDE, people usually choose H alpha norm, but some people also choose like C alpha norm. Okay, so with a mixing rate function, then our result says that if V is mixing with rate function H, then the dissipation time tau star is bounded about by 1 over kappa times H kappa. Here the function capital H kappa is explicitly given by this through this formula. So you can see it once the rate function H is given, then you can solve this capital H through explicitly. Okay, this formula looks complicated, but for most of the case, people are interested in the rate function H with exponentially decaying rate. So if H is exponentially decaying, for this this formula actually tells us that the tau star can be bounded about by C times log kappa square. So this estimate gives us this upper bound of tau star. Okay, first we actually we got the rate. Our estimate only got like tells that the rate is C divided by kappa over 2 power of delta. But later I improved this in my thesis to be C times log kappa square, and this estimate is the same as the result obtained by Tarek and Michele Cotizzilati at the same time at 2018. Their result also suggests that if H is exponentially decaying, tau star is log kappa square. It's bounded about by log kappa square, and the estimate of the dissipation time. This estimate log kappa square is the best rate so far. So as we know so far. So and this implies that the L2 energy decays at C times e raised negative ct divided by log kappa square times the initial L2 norm. So this estimate implies the decay of the L2 energy in this rate if V is exponentially mixing. And we can prove similar result holds if the diffusive term is replaced by bi-Laplacian or fractional Laplacian. So this can be generalized to some other diffusive operators. So then flows are called dissipation enhancing flows if tau star is of little o of 1 over kappa. So from my previous slides, we can see that relaxation enhancing flows are dissipation enhancing, and mixing flows are dissipation enhancing. So it would be good if we can construct some mixing flows, right? Especially mixing flows with exponentially mixing rate, exponential decaying mixing rate. However, regular mixing flows with exponential mixing rate are not easy to construct. The more regular the flow, the harder it is to mix the tracer optimally. But there are some other flows, like shear flows, which may be time independent and are very easy to construct. For these shear flows, the corresponding transport operator V dot gradient has a large kernel. However, dissipation enhancement can also be obtained by projecting out the kernel. So some result can be found by the work of Benjosin, Cotizzilati, and Wei. So let me explain this a little bit. Like for shear flows, we can see like for the if we in the transport advection diffusion in the corresponding advection diffusion equation, so it's writes like it is written like this. So if for this advection diffusion equation, if the initial data only depends on y, right? Then you can see the flow makes no effect on the in the diffusion in this diffusion process. So that means this initial data lies in the kernel of the shear flow. So it cannot it will not enhance the dissipation for all the initial data, but by projecting out the kernel, we can still prove a dissipation enhancement result. So why are we interested in the dissipation enhancing flows? Because they would bring some nice result to the nice effect to the when adding to some known systems. So it, for example, it may prevent finite time blow up due to concentration. For example, in the aggregation diffusion model, like Keller-Segal model, it is for Keller-Segal model, usually like in 2D or 3D, usually there would be like blow up of solution, right? But if we add this kind of flow to this system, one can prove if the flow is large enough, then there will be global existence of the solution. So this has been studied by Kislev and Xu, He, Beizhou, Hope, Rodrigo, and Zeng Zhangzi, and Feng Shiwang. It may stabilize the flow. For instance, in with damping for Euler, it has been studied by Beizhou Masbodi, Beizhou Codizzelati, and Wei Zhang Zhao. It may prevent phase separation in Canhillier equation. Like for Canhillier equation, usually there would be there would be the steady state is in the steady state we can see phase separation. But if we add the advection, diffusion, add the mixing flow to this system, we can prove the phase separation would be prevented. This is done by Feng Year and Tifeld. It may ensure global existence for the model of flame front propagation, like Kuramoto Sivashinsky Equation. It has been studied by Feng Mazzucato, Codizzelati Dossi, Feng Mazzucato, and Feng Shiwang. So today, for the second part of my talk, I would use I would mainly focus on the applications to the Kuramoto Sivashinsky equation. So first, let's recall what is the Kuramoto Sivashinsky equation. So Kuramoto Sivashinsky equation is a model for long wavelength instabilities in dissipative systems like flame front propagation, reaction diffusion equation. So we mainly study the problem in 2D or 3D periodic box, and the length of the box in each direction may not need to be the same. So I just use L1, L2, or L3 to represent the length in each direction. Usually the equation has two forms. One is the integral form, which is written as partial t phi plus a half times gradient phi square equals minus Laplacian square phi minus Laplacian phi. And if we denote the vector u to be the gradient of phi, then we also have the derivative form of the equation, which is partial tu plus a half times the gradient of u square equals minus Laplacian square u minus Laplacian u. So we can see like this equation is like, you can see if we look at the derivative form, this nonlinearity part is like a Burgers type nonlinearity, and it may have instability at large scales. For 1D, this equation is relatively well understood. We have the global well-posedness and the analyticity for T positive. There are many challenges in the analysis in 2D or 3D, because you can see like for the linearized, for the right-hand side, the operator reads as minus Laplacian square minus Laplacian, right? For this operator, there might be unstable modes for this linearized operator if any period Li is greater than 2 pi. Because if you look at the if you expand this operator in each Fourier frequency, you can see that this is going to be minus k squared to power 4 plus k squared. So if k is small, then this should be positive, right? So this may result in exponential growth when Li is greater than 2 pi. And since it's since we have Laplacian square, so this is a fourth order. This is a biharmonic operator. There is no maximum principle, so there is no a priori L infinity bounds. And when we do energy identity, we can see that there is actually no a priori L2 bonds. Actually, there is no a priori LP bonds for any P. So there's some previous result on the global existence in 2D or 3D, like global in time well postness for thin domains, which is obtained by Cell Tabado, Taboda, Molinate, Benekar, Kuka, Russian, Zeni. And for small data in H1 or Wiener algebra, one green mode in each direction. This has been done by Ambrosi Mazzucato. So in general, like we do not have global existence. Like the global existence only achieved for spatial domains or for small data. So our result with under Mazzucato, we find that we worked with the integrated form of the Kuramoto Sivashinsky equation. We find that if there are no green modes, that means Li less than 2 pi in each direction, then we have global in time existence of mild solution for small data in L2. And this result can be extended to LP for any P between 1 and infinity. If there are green modes, we prove that the global in time existence can be achieved for large data in L2 if the dissipation enhancing flow V is added. So in this case, we actually look at the so-called advective Kuramoto Sivashinsky equation. So I'll call this AKSE. We can prove that as long as V, the amplitude of the dissipation enhancing flow V is large enough, then we can have global existence for this system. So actually, this model is first raised by Dandeker and Collins in 1995 to model the flame propagation in premixed combustion. In both cases, our discussion are based on the continuation criteria is based on the L2 norm. So actually, for the second part of our result can be written in a more generalized form. Like we can write the fourth order equation in this way. So we use n phi to represent the nonlinear term. Then we can prove as long as phi, the nonlinear part satisfies the condition 1 and 2. Condition 1 says that the L2 norm, condition 1 says that for any phi in H2, the integral of phi and times n phi, the nonlinear part, is bounded by 1 minus epsilon times epsilon 0 times the Laplacian phi L2, the L2 norm of Laplacian phi square plus some function f, of the L2 norm of phi L2 norm of phi. Here epsilon 0 should be something strict greater than 0 and less than 1. For any condition 2 says that for any phi in H2 there exists a non-negative constant C0 such that, and a non-negative function g such that the L2 norm of the nonlinear part n phi is bounded by C0 times the L2 norm of Laplacian phi square plus some function g of L2 norm of phi. So for this generalized form, if this nonlinear term satisfies these two conditions, plus if the linear lim sup of these two functions f and g satisfy with this square root f plus g divided by y is bounded above by infinity as y goes to 0, then the global in time bound on the L2 norm of the solution can be achieved provided the dissipation time of V is small enough. Okay, this generalization is inspired by the work, the paper by Year Xu Zelatos, where they discussed the case for the Laplacian operator. Let me briefly introduce the strategy of the proof. So to prove the global existence of this system, we first project out, we first project onto the mean zero functions, call it psi. Mean, we can prove mean of phi is not preserved, but can be controlled. Then we prove that, we prove short time existence of mild solutions, psi, of the projected advective Kuramoto Sivashinsky equation in a suitable adapted space with delta in L2. And then we prove this psi is also this mild solution, psi is also a weak solution in L2, in the sense L2, H2 for any T positive. And also this weak solution satisfying energy equality. And then we show that if the dissipation time of V is small enough, there is a priori exponential energy decay of the L2 norm of psi by energy estimate. And then we conclude using the continuation principle based on the L2 norm, we can have global existence. Okay, this is the result. This result actually works for 2D and 3D as long as we can add some dissipation enhancing flows with large amplitude to this system. But as I mentioned before, usually for the dissipation enhancing flows, we use the mixing flows, which is time dependent and very complicated to construct. So instead, we want to use some simple flows. So we want to, for example, we want to use shear flow. We want to add a shear flow to this system. So in 2D, we can prove that if V is a shear flow, the global existence of solutions can also be achieved when linearly green modes only appear in the direction of the shear. This is a joint work with Cotizilati, Dossi, and Mazzucato. So how does it work? Such shear flows, as I mentioned before, such shear flows are dissipation enhancing in some subspace, and the kernel space is one-dimensional. For the component, in the kernel space of the flow, this can be reduced to a modified one-dimensional Kuramoto Sivashinsky equation. The L2 norm have uniform in time bound in the absence of green modes. That means we need to restrict L2 less than 2 pi. For the component orthogonal to the kernel, the L2 norm is bounded due to the property of the dissipation enhancement. So let me go to some details of this. So first, let me introduce the decomposition in this way. Like say, F is in L2. We denote F average to be a function of Y, which is to say like to just take the average in the X direction. So F average is only a function depends on Y, and we denote F not equal as the remaining part. With this notation, the advective Kuramoto Sivashinsky equation can be decomposed as these two equations. The following two equations, you can see that for equation 1 is a one-dimensional equation, and for this you can see it's actually a one-dimensional Kuramoto Sivashinsky equation with some coupled term, with some nonlinear term coupled with phi not equal to, right? So we can call it's actually a 1D modified Kuramoto Sivashinsky equation. And for equation 2, it's we have the flow, right? It looks complicated, but since this flow has a effect of dissipation enhancement, it can control all the nonlinear, all the growth induced by the nonlinear part on the right. It can control all this. So equation 2 actually is for equation 2 we are fine, since as long as we can prove this operator. If we can prove this operator has the dissipation enhancing result, then we are good. And for equation 1, since it's a 1D modified Kuramoto Sivashinsky equation, if this operator, like partial y force plus partial y square, this is strict positive, then we can also have a global uniform in time bound of the L2 norm. Then we are also good. So to make this operator to be strict positive, we have to ask to restrict the domain to be like to have no green modes. That is to say L2 is strictly less than 2 pi. That's why we need to put this condition here, restriction here. Okay, so if we put this restriction, then for equation 1, we are happy. We have the uniform in time bound of the L2 norm of phi average of this. We have a global uniform in time bound of this estimate. Then for equation 2, we need to focus on proving the dissipation enhancement of this operator. Okay. So to prove the dissipation enhancement of that operator, so first let's recall that if the operator is if we denote h kappa as uy partial x minus kappa Laplacian, so if the diffusive operator is Laplacian, it has been proved by Beijou's Cotizelati in 2017. They proved the rate of the dissipation enhancement using hyperellipticity, and later we in 2018, he proved it by using some Gerhardt-Prust type estimate. In our case, our h kappa is uy partial x plus kappa times Laplacian square. So it's now the diffusive operator is Laplacian square. We first established the dissipation enhancing rate of the shear flow for the hyperdiffusive operator by applying the Gerhardt-Prust criteria, and we get this semigroup is actually can be bounded has this estimate, like it can be bounded by c times e raised to negative ct times kappa raised to m divided by m plus 4. And here, what is m? M is the order of the critical points of u. Like for example, like okay, here is a prototypical example. Like say uy, the shear flow is the shear profile is written as sine of y divided by sine y to power l here with some normalizing coefficient here. 2 pi divided by L2 is just some normalizing coefficient. For this shear profile, we have m is the maximum of L and 2. So for this shear profile, the best rate can be achieved is c e raised to negative ct times kappa raised to 1/3. So this is our result. Recently, Simin He proved that for h kappa written like this, uy partial x plus kappa times minus Laplacian x raised to power gamma plus kappa times minus Laplacian y raised to power gamma. Here gamma is can be some fractional number. Gamma is ranging from 1/2 to 2. This was studied by Simin He recently using hyperellipticity, and he also get some rate of the corresponding. He gets some rate of the corresponding operator for the explicit form. Rate I forgot, but I think when gamma is 1, his result is corresponds with what we got in 2018, when gamma is 2, his result is the same as what we got in this one. So actually, I think our method can be easily generalized to the fractional Laplacian case. Yeah. So we can get the same result. Okay. So for when we do the when we estimate this semigroup, we expand this in the in each Fourier frequency OX. So we denote H. We expand this as H kappa k. K is the frequency in the x direction. So then this can be written like kappa Laplacian k square plus I k times uy. Laplacian k is just minus k square plus partial yy. So we also use the Gerhardt-Prust type estimate, which says that if H kappa k is M accretive, then the semigroup e raised to negative H kappa kt can be bounded by e raised to negative t times some function psi of H kappa k plus a constant pi over 2, where this function psi of H kappa k is defined as the infimum of the norm of the of H kappa k minus I lambda act on G for any G in the domain of H kappa k. So by the Gerhardt-Prust type estimate, we only need to establish a lower bound for this function psi of H kappa k. So to use the Gerhardt-Prust type estimate, we need to first check H kappa k is M accretive. So this is not difficult. So we can prove we need to prove it is M accretive. We need to first check the left open half plane is contained in the resolvent state. This is simple, since the real part of the H kappa kf and of the inner product H kappa kf and f is positive for any f in the domain. And for any real part for any lambda with real part positive, we also need to prove the norm of the inverse operator of H kappa k plus lambda I is always bounded up is always less than the inverse of the real part of lambda. This since this is also very easy to check, since we always have since we find that the real part of this inner product always have can be bounded above by this and bounded below by real part of lambda times H times the L2 norm of F, since H is positive. Since we have this observation in the first part. So it's easy to check H kappa k is M accretive. So we can happily use the Gerhardt-Prust type estimate to estimate the function, to use the bound for the function psi H kappa k to bound the decay of this semigroup. Okay, so as long as we can prove is dissipation, that flow is dissipation enhancing for in the corresponding advection hyperdiffusion equation, then to prove like then to prove the L2 norm is can be bounded, it's just the same as our previous result, as the case when we use the dissipation enhancing operator, right? So that solves the case for in 2D. So what about in 3D? So in 3D, the shear flow would not work, because for the kernel space of the shear flow in 3D, it is going to be two-dimensional. So if we look at the the Kuramoto Sivashinsky equation, like for the kernel components, the kernel components of the kernel components now reduced to a modified two-dimensional Kuramoto Sivashinsky equation. As I mentioned, the two-dimensional the global existence for the two-dimensional Kuramoto Sivashinsky equation is not known; it's open. So, so in this case, we want to use some other flows. We want to construct some other flows for which we can. The kernel space is smaller, and we can still prove that it has in the by projecting out the kernel space, we still have the dissipation enhancing result. So in 3D, so we construct this so-called planar helical flow, which is defined as uy, like say in 3D, like we use x1, x2, y to represent the position in the 3D. The flow is defined as uy, sine y, uy, cosine y, 0. Here, okay. 2 pi divided by, again, like we use 2 pi divided by L3 as some normalizing parameter, a coefficient. So this is a joint work with Bingbing Shi and Weiko Wang. So we first, we introduced this flow in 3D, and we studied the rate of dissipation enhancement for such flows. Like, actually, we studied the like in this case, our H kappa, the corresponding H kappa linearized advection diffusion operator is just kappa times minus Laplacian square, right? Here I plus uy sine y partial x1 plus uy cosine y partial x2. Here, we in our work we only checked for the case when gamma is 1 or 2, like we checked when the diffusive operator is Laplacian or bi-Laplacian. We checked the rate of the dissipation enhancement. Actually, this result can be this result can be generalized for any gamma between 0.5 and 2. The application to the global as long as we can prove like this operator has some dissipation enhancement result, then the application to the global existence of the advective Kuramoto Sivashinsky equation works similarly as the shear flow case, right? And we can also use this. We can prove like as long as like for the component in the kernel space of the flow, as long as L3 is less than 2 pi, we have the global existence. And another interesting application of this flow is to we apply this to the 3D Keller-Segal equation. So previously, Siming He and Jacob, they proved that they use the shear flow to the 3D Keller-Segal equation, and they proved that the global existence can be obtained when the initial mass is less than 2 pi. But now, if we apply this planar helical flow, the 8 pi, the 8 pi restriction of initial mass can be removed. Okay, I'll end my talk by pointing out some future directions. So we can see that the planar helical flow is like an extension of shear flow from 2D to 3D. So in higher dimensions, say like any d greater than 4, can we construct some steady flows which are dissipation enhancing in some restricted subspace, and the kernel space is still like not too large, or say like it will be good if it's just one-dimensional. Why are we interested in this? Because such high-dimensional flows, like we want to apply these flows to the sampling process. We want to use these easy constructed flows to apply this easy constructed high-dimensional flows to accelerate the convergence of Markov chains and speed up the sampling process. Another possible direction is, can we prove some other flows like okay, it is proved that large amplitude cellular flows with small cells are good short-term mixers on torus, on 2D torus. This is proved by Year, Xu, and Zlatos. But they use some stochastic method, and the result only works for when the diffusive operator is Laplacian. Can we get a similar result when the diffusive operator is bi-Laplacian or fractional Laplacian? I think this is also an interesting project in the future. Okay, that's the end of my talk. So thank you for your attention.
Thank you very much for a very nice talk. Questions?
Hi, Anne. Nice talk. So, what is known in the case, and what if you have any ideas for the case of the whole plane or the whole space?
So you so you want to know the dissipation enhancement result for the when the space is when the domain is RD, right?
Right, exactly.
I do not know so by now, but I think if we so since in RD we do not have exponential, like by general energy, by the element just by energy estimate we cannot get exponential decay, right? Because we do not have the Poincare inequality, but we can have some polynomial decay if we assume there is some some decaying factor, right? I hope we can still in the rate of the polynomial decay. I think it can still be improved if we add the if we assume the flow is mixing in some sense plus some other conditions, growth conditions on the gradient of the flow, right? But I think we can still get some kind of improvement of the rate, but I haven't figured it out so far.
Okay, thank you.
Anybody else? Are there any?
Can I comment briefly if no one has?
Yes, please.
I don't know. I think the whole space thing is a lot of fun. I don't know if it's possible. There's an old paper of Andre that goes in this direction. But I mean, the issue is you could have a positive blob very far away on one side and a negative blob very far away on the other side. And I mean, these things could go further and further. And the flow just needs time for these two to mix. So I don't know if it's going to work out, right? But there's a paper of Andre and I thought about it a bit. I don't know what to do. It's a fun question. Right?
Okay. Oh, so you think it's not possible?
Not as stated.
Oh.
But I think it needs some modification, right? But
yeah.
Questions? Okay, let's thank Yuanyuan again. Thank you.
Okay. Thank you for your listening.
We'll close today's session. Thank you.